The next lesson is on discrete time systems, part 2. Let's look at some more examples of discrete time systems. So let's see moving average. So this one averages latest n values. What does that mean? For example, if I want to average current value and the past value, I can say my y of n is just equal to x of n plus x of n minus 1 divided by 2. So I'm just averaging the current value and the previous value. And in general, if I want to average capital N values, then I can write it like this: capital xn plus xn minus 1, so on up to xn minus capital N minus 1 divided by capital N. Right? So what does that mean? So what's the use? It is used for smoothing a function. For example, you see there is let's say it's originally a constant signal, but there is a lot of noise in it. I want to smooth it out. I can simply apply a moving average filter or a moving average system. I can pass it through that, and the output will be almost like 1. It will be almost 1. So means that is the use, that the output will be almost constant. This is used for removing noise or removing a lot of variation. Another example of a system is an accumulator. What is an accumulator? It sums all the values till the current value. So let us say I want to find, okay, this will be equal to x of n plus x of n minus 1 plus x of n minus 2, so on up till infinity. But actually, if your signal is finite, if the input is finite, then you can assume that all previous values were 0, and then your yn will be also finite. What if I give a constant input? Okay, let us look at two examples now. One example is a sinusoid. Let us say I have sine of 2 pi n upon 5, right? This is my x of n. What will be my y of n? My y of n will be, let us say if it starts from n equal to 0, then my sinusoidal will be increasing like this, which means essentially this thing, and my y of n will be summing it over, and after one complete cycle is over, then my y of n will become equal to 0. Then again it becomes positive, negative, the sum will become positive and then 0. So this is like an integrator, right? It's like an integrator. Okay, but what if I give a constant input? If I give just, let us say, unit step u of n, which is 0 before 0 and after 0 it is always 1. So you know it's an integrator, so the output will keep on increasing with n. So which is not a nice thing, because the system will become unstable. This brings us to the property of stability. What is the meaning of stability? A system is BO stable, which means bounded input, bounded output stable, if a bounded input sequence produces a bounded output sequence. So let's say we saw the example of constant input given to an accumulator. We saw that this is not bounded. Even if the input is bounded, your x is always equal to 1, which means less than equal to 1. Your x for all n. Okay. This means that my y of n is equal to basically n always, right? So which means this is not bounded, because as n keeps increasing, my y of n also will keep increasing. So this is the test. take an xn such that the xn is magnitude is always bounded by a finite number bx for all n. Then we have to see if there exists a by which is also a finite number such that y of n is also less than equal to by, is bounded by that by. If you can find such a by, then you can say that yes, my system is Bibo stable. But if you cannot find any such by, then it cannot be Bibo stable. So is an accumulator stable? Let's go back to the accumulator example. If I give a constant input, my x of n is bounded, right? My b of x is equal to 1. Okay, right? But my b of y does not exist because my y of n is n, and as n keeps increasing, this is unbounded. I cannot find a by, so accumulator system is not stable. A moving average system, is it stable? Yes, let us say if my x of n is always less than equal to b of x, then my y of n, which is equal to summation of x n minus k goes from 0 to n minus 1 divided by n. So I know that this is always less than equal to b of x. You should take this thing. And summation this is always less than equal to 1 upon capital N times bx. So which means my y of n is also bounded by bx. So yes, this is a stable system. Okay, now another property of systems which is useful is time invariance. So the intuitive understanding is like this. If I pass some sequence xn to a system today, I get some output. Now if I pass the same sequence as an input to the same system tomorrow, I get a different output. That is not, this means the system is changing, or this means the system is not time invariant. It depends on time. So that system is not time invariant, right? So I have taken, for intuitive understanding, I have taken today and tomorrow, but it could be instants n minus 1, like very close instants. Okay, let's see the formal definition of time invariance. A system is called time invariant if given an input sequence x of n, if I pass it through the system f, then I get the output sequence y of n. Then if I pass the same input x n minus n, which means if I have a delay in my inputs and I pass the delayed input to the same system, the output should also be a delayed version of the outputs, right? X of n minus 1 is a delayed version of x of n. So the output of this system should also be a delayed version of my y of n, which was the output without any delay, right? Another way to write it is this. So if I pass an x of n to my system, this is my y of n, right? This is my sequence, and the n minus nth entry of this sequence, and this thing is I have passed a delayed version of the input, so this is my y dash. So my y dash n is simply n minus nth entry of the sequence yn, which is obtained by this, right? So this is how time invariant system is. Okay, let us see in the figure. If my x of n is this and my y of n is this is given. Now I ask you, if my x dash n is this, which means a delayed version. So this means this is simply delayed by 3 equal to x n minus 3, right? Now, what should be my y dash n? So if this is a time invariant system, this should be simply equal to y of n minus 3, right? Which means this will come here, this will come here, and this will come here. This is 5. Right? So this is the meaning of this is for a time invariant system. But if it is not a time invariant system, then you won't get this. Okay. Can you suggest a system that is not time invariant? Okay. Sampling. Okay. Let's see how sampling works. Let's say this is my input sequence, which is 1, 2, 3, 4, 5. And if I downsample it by 2, what will be the output? The output will be, okay, let's say we start from the 0th entry, 1. I skip this, or I drop this, and I get 3. Then I drop this, I get 5. Right? This is simply downsampling. Now I add a delay. So now my x dash of n is xn minus 1, which is 0, 1, 2, 3, 4, 5. Same sequence, but delayed by this input, right? So what will be the output? The output will be, okay, 0. And then I drop this, 2. Then I drop this, 4. So which is not equal to a delayed version of y of n. This is not equal to y of n. So means my y dash of n is not equal to y of n minus capital N. That is why this is not a time invariant system. Let's look at another system, another property of systems called linearity. This is, so let's see the basic intuitive understanding. It is desirable that the output scales proportionally with the input, right? If I scale up my input, my output should also scale up by the same factor. This is called a linear system. A system is said to be linear if and only if f of x1 plus x2 is equal to f of x1 plus f of x2. And another is the scaling part. So this is it's invariant to addition of signals and invariant to the scaling of signals. This is the linearity. The references for this part is same OpenIM chapter 2 section 2. Thank you very much.